Hello everybody, Harry from GMAT Ninja here and welcome back to our GRE Quant series. In this video we'll be looking at statistics, but as you can see written up behind me, we've got looking at the second half of the statistics. In the first video we took a look at means, medians, ranges, combined averages and a couple of other things. In this video the bits that we're going to be getting into are some of the ones that you might call the more complicated side of statistics. We'll be looking at how the GRE talks about standard deviation, about percentiles and normal distribution, and we'll still get back into several of these questions where there is algebra but it's disguised as statistics. The question might talk about standard deviation, for example, but really it's an algebra question. You just need to interpret what's in the words and get to the algebra so that you can work it through. So I've got 7 questions for you today, ranging from relatively basic. What I'd say about this video is if you're aiming for something up to a 150, you probably don't need the things in this video. I'd go and focus my time on the algebra and the geometry and the things that are going to make up more of the test. If you're aiming for something in a 160, hovering around a 160, yeah, you're probably going to need this stuff, and hopefully we're going to have something for you today. And then I'm going to ramp up the difficulty right at the end of the video, and those of you that are looking for a 165 plus, stick around. The final couple of questions are going to have something for you there. All right, I'll get the first question up on the screen, and as we do every time, I'm going to give you about 1:45 to take a look at it, have a think about the question, and then we'll take the question away so we can go through the solution and talk about the context on the board together afterwards. So I'll get the first question up on the screen for you now. Best of luck, and I'll see you back here very soon. All right, as always in these videos, if you need a little more time to have a think about the question, now's your chance to pause it, keep working on the question, and then restart the video, and we'll still be here when you get back. So we're going to take the question away now so that we can take a closer look at this together. Now, first thing, hopefully to reassure you, there is a formula to calculate the standard deviation. You don't need it. We're not going to put it up on the board here. We're not going to talk about actually calculating the standard deviation because I haven't seen a question on the GRE in any of the practice materials where that's necessary. I know that it says here, I know quantitative comparison question, we're going to compare the standard deviations of the numbers in these two lists, but we can do that using quite hand-wavy methods. We don't need to calculate the standard deviation here. So a very rough definition that we're going to think about over the next few questions and how the GRE talks about the standard deviation is you can think about the standard deviation as about how spread out the numbers are within a set. Or maybe you could think about it as the average distance from the mean within the set. Now, it's not that. If you walk into a statistics classroom and say something like that, that's not going to be right, but it'll serve our purpose on the GRE. So it's either how spread out the set is or sort of the average distance from the mean if you want a kind of numerical value for it. But like I say, don't think of that as a technical definition. It's really not right, but it'll do the job for us now. Okay, so in this question, like I say, we're not going to calculate the standard deviation. What I can say about this is I don't know the numbers, but we're going to certainly don't know what the standard deviation of the numbers is in list S, but I'm comparing it. Which one of these sets is more spread out? Now, the thing to notice here is I know all the numbers in list S, know all the numbers, know how spread out things are. In list T, I only know about two things. I know the smallest number, I know the largest number. I don't know anything in the middle. And so that means that I am going to struggle to figure out how spread out the numbers are in list T. So I'm going to give you two scenarios. One of them's, well, that's going to help us get to an answer here. So the first one, so the difference between 131 and 143 is 12. The range of list T is 12 and the range of list S is 12. So what I could do is make list T mirror list S. So the smallest number in list S is 104, smallest number in list T is 131. Then the next number in list S is also 104, so I'll make the next number in list T the same as the smallest one. Then in list S, I go up 2. So in my imaginary list T, I'm also going to go up 2. And I'm just going to repeat this process. I'd go up 2 again to get to 108. I'm going to go up 2 again. So I'll go up 2 again here, then I'd go up 4, so I'll go up 4 here, and finally I'll go up 2 again, and I've got the 143, which is the top number. So if this was list T, well then the numbers are equally spread out, and so the standard deviations would be the same. But I don't know that. It could just as well be, this is my second imaginary list T, I've got my smallest number, I've got my biggest number, but then if you sort of split the difference here, 137 is exactly in the middle. And so every other number in the list could be 137. And so I'd end up with 5 137s, a 131, and a 143. Right? And so now what this second list says is that these numbers are far less spread out. All of these are the same. They're right in the middle. The average of this list, the mean of this list would be 137. And so, as we talked about, you can think about standard deviation like the average distance from the mean. Well, the distance from the mean of all these 5 numbers is 0. Okay, I've got a little bit on the end. But the spread in this second list is going to be so much smaller than the spread in this first list. And we said that the spread in this first list was exactly the same as the spread in list S. So the standard deviation in my first imaginary list T is going to be the same as my standard deviation in list S. My standard deviation in my second imaginary list T is going to be far smaller than the standard deviation of list S, which means that I can't tell. So they could be the same. I could possibly, I don't know, not figured this out. I could possibly come up with a third imaginary list T where it's more spread out than the standard deviation of list S, but I don't need to do that. I've got one where they're the same, one where list T is smaller. So in this case, quantitative comparison question, I can't tell which of the two is bigger or whether they're the same. So the answer to this question would be D. So as you can see here, I didn't do any calculation. I'm not going to put the formula for standard deviation up here. We're not going to calculate the standard deviation of a set of numbers. But what we can do is use the information that we've been given and think about how spread out these sets are and what the average distance from the mean is in order to come up with different scenarios that in this case show me that I can't tell the difference between them. And that's about as close as you're going to have to get to calculating the standard deviation. All right, so there's a couple of other ways the GRE is going to talk about standard deviation. We're going to get through them in the next couple of questions. This is one of them. And when you're asked sort of which set has a greater or smaller standard deviation, there are ways of thinking about it using those ideas of spread that are hopefully going to get you through them without significant calculation. I'm going to get the next question up on the screen now. We'll give you another minute 45 or so to take a look at it, and I'll see you back here to go through the next question soon. All right, now's your chance to pause it if you want a little more time to look at this one, but I'm going to take the question away so that we can take a look at this one together. All right, so in this question, I'm going to take the ideas forward that we were talking about in the last question. Standard deviation, you can think about how spread out the numbers are in this set. So in this case, we've got a bunch of variables here. I don't actually know what the numbers are in this set. So even if we had the formula, we're not going to be able to calculate something. But I'm going to need to do something in order to try and figure out whether I can tell whether quantity A or quantity B is bigger here. So what I'm going to do is I'm going to look at PQR just as an illustration. I'm going to say, well, what if P was 5, Q was 10, and R was 15? They might be. They're probably not going to be those numbers. I'm just giving you them as an example. And so I can say that the set PQR would be the set 5, 10, 15, and that set's going to have a standard deviation of 5. And now let's see what happens if I look at quantity A and quantity B here. So quantity A, what I'm doing is adding 10 to each value in the set. And so if I do that, I'd add 10 to each of these numbers, I'd end up with 15, 20, and 25. Now go back to that kind of hand-wavy definition that we were giving you earlier. Standard deviation, think about it about how spread out the numbers are in the set. So between the 5 and the 10, there's a gap of 5. Between the 10 and the 15, there's a gap of 5. The numbers have a gap of 5. They're spread out with a gap of 5. Come down here, I've added 10 to each thing. Well, 15 to 20 still has a gap of 5. 20 to 25 still has a gap of 5. I haven't changed how spread out the numbers are. I've just taken them all and shifted them up by 10. And so I haven't changed how spread out they are, so I haven't changed the standard deviation. Standard deviation of this P plus 10, Q plus 10, R plus 10 is the same as the original. It's still 5. And so we can say quantity A is going to be equal to 5. So now I can do something similar with quantity B to test against that. If I doubled P and doubled Q and doubled R, then 5, 10, 15 is going to become 10, 20, 30. Okay, now the gap is not 5 anymore. The gap between the numbers has doubled. And so I have taken the numbers and yes, I've doubled them, but I've also doubled how spread out they are. And if standard deviation is a measure of how spread out the set is, and I've doubled how spread out the set is, I've doubled the standard deviation. So by multiplying the standard deviation, or multiplying each item in the set by 2, I've doubled the standard deviation, and the standard deviation of that third set, quantity B, will be 10. So quantity B is going to be 10. Quantity B is bigger than quantity A, so the answer to this question is going to be B. So when you're given a set of variables, P, Q, R, and you're told the standard deviation, if I add to each of the numbers in the set or subtract, all I do is shift the numbers left or right along the number line. I don't change how spread out they are. So adding or subtracting to each of the numbers in the set is not going to change how spread out they are, obviously, as long as you're adding or subtracting the same thing. If you add or subtract different things, okay, the numbers might be more or less spread out, but that's not really what we're looking at in this question. If I add the same number to each item in the set, I just shift it up or down. I don't change how spread out it is. If I multiply the numbers in this set, well, in this case, I doubled them, so they all got bigger, but I also spread them out more because doubling all the numbers doubles the spread. And you could think about that in terms of division as well, or multiplying by a fraction. If I multiplied everything by a third, well, then the standard deviation would shrink by a factor of 3. I would multiply the standard deviation by a third. And so there's a difference between addition and subtraction and multiplication and division. Addition and subtraction does not change the standard deviation. Multiplication and division does. All right, and that will hopefully be enough to get you through this style of question. All right, I've got one more standard deviation style question for you. This one's a bit more of a word problem. So take your time, have a close read of the question, usual minute and 45, and I'll see you back here soon. Okay, pause here if you want some more time for this one. But let's take the question away so that we can work this one through. All right, so this is a question. It talks about standard deviation. We're not actually going to use standard deviation in the solution. This is one of those algebra disguised as statistics questions. So yeah, a lot of text here, and it talks some statistic terms. It talks about standard deviation and means and all the rest of it. And so please don't let the text here intimidate you. We just need to understand what's going on so that we can get to an answer. So there's two ways that I would think about this. One is algebraic and one's a bit more graphical. I'm going to go down the algebraic route first, and then I'll show you the graphical method. It doesn't really matter which one you go down. Both of them are about the same. It's just which one you feel more comfortable with. All right, so we're told up in this first line, one student is 2.6 standard deviations taller than the mean. And then I'm going to jump a bit, and the first student has a height of 204 centimeters. So 2.6 standard deviations taller than the mean equals 204 centimeters. So I could represent this as something like the mean plus 2.6 standard deviations, I'll call them S, is equal to 204. Then I could say, look at the second student. Another student is 1.8 standard deviations smaller than the mean, and that student has a height of 138. So the mean, take away 1.8 standard deviations, is going to equal 138. And I hope you can see very quickly we get to a set of simultaneous equations, and we just now need to go and solve these and find out what m is. But the way they're set up, we're going to find s first, and then we'll get to m. So the way I'm going to do it, I'm going to leave that first one alone. I'm going to take that second one. So if I call that equation 1 and that equation 2, I'll take that second one and multiply it by -1. I'm going to get negative m plus 1.8 standard deviations equals negative 138. I'll just rewrite number 1 underneath it. M plus 2.6 standard deviations equals 204. And then I'll add those two equations together. The m's will cancel out. I'll end up with 4.4s, and that's going to equal 66. Divide by 4.4 on both sides, I'm going to get s is equal to 15. And so that's my standard deviation. And I can now go and put that back into one of these original equations, and that'll get me the answer for m here. So I'm going to choose to put it back into that second one. And so m minus 1.8 times my s value, that's 15, is equal to 138. 1.8 times 15 is going to be 27. And so m is going to be 138 plus 27, which will give me 165. And so the answer to this question's going to be C. Now, just very quickly as an aside, some of you might be asking, why did I multiply the second equation by -1? That's just, it's a standard way that we deal with simultaneous equations. I always want to be adding the simultaneous equations. Reason for that doesn't have anything to do with simultaneous equations, but it just means that I'm standardizing what I'm doing so that if I deal with simultaneous inequalities, I'm always adding them. I'm always adding simultaneous equations. I'm always adding simultaneous inequalities so that I'm doing the same thing every single time. And it just means that I don't make a mistake. So just if you're asking, why did you multiply that by -1? Why did you not just subtract the two equations? There is some reasoning behind it, but that's more to do with how we deal with algebra rather than statistics. But since we're here, that's what I was doing there. All right, so one way of looking at the question, treat them like simultaneous equations, and I've got my answer there. The other way, as I said, we could look at this a little more graphically. So if I draw myself a bit of a setup here, a bit of a set of bars, and I probably don't need those bits at the end. All right. Now I'll say the mean. At this stage, I know we've answered the question, but at this stage, I don't know what it is. Okay, the mean, and then I'm going to start going. There's the mean plus 1 standard deviation. There's the mean plus 2 standard deviations. And I can do the same here. The mean minus 1 standard deviation, the mean minus 2 standard deviations. And what I was told was one student is 2.6 standard deviations above the average. So if there's the mean plus 3 standard deviations, then in there, mean plus 2.6 standard deviations, that's going to be 204. The other one was 1.8 standard deviations below the mean, and that was 138. I need to rub that out to give myself some space. And what we can see here is that the gap between these two, well, in terms of the numerical values, 138 to 204, that's 66. But the gap between how many standard deviations there are Well, that's 4.4 standard deviations. And so again, we're almost jumping to this stage. 4.4 standard deviations is the same as 66, which gives you a standard deviation of 15. And then we can just work our way into the mean, and that'll give you the value of the mean at 165 that we were looking for. So like I said, you can go algebraic, you can treat these as simultaneous equations, or we can treat this as a bit of a bar and use this graphical method. Both of them are going to get you to the same answer in the end, and which I don't think either of them are, one of them's particularly fast than the other. So which one you choose, entirely personal preference, and which one helps you interpret and understand the question more easily, more effectively, and more accurately. All right, so that's all I've got for you on standard deviation for today. Like I said from the start, we don't need to calculate it. Think about it in terms of measure a spread, or very rough here, the average distance from the mean, and that'll give you just about all you need to answer the standard deviation questions you're likely to see on the GRE. Next bit we're going to get into is about percentiles. So I've got a couple of questions for you here. As usual, I'm going to throw the first one up on the screen, give you nearly 2 minutes to take a look at it, and I'll see you back here to work through this one very soon. All right, if you want some more time to think about this one, pause the video here, but I'm going to take it away so that we can look at this one together. All right, so we've dealt with standard deviation. I'm going to put that to one side. Now we're going to look at percentiles. So before we jump into this question, I just want to talk about what percentiles are for a second, because it's one of those terms that makes people freeze. They're not really sure what to do with it. So a percentile, all that we've done here is taken the data and chopped it up into 100 equally sized chunks. So in this case, I've got 8,000 students. 1/100th of that would be 80. And I take those 80 chunks and we can say things about them. For instance, if you were in the, let's say the 99th percentile, right, what that means is that your score in the exam is better than 99% of the other people that have taken the exam. So you can say that you are somewhere between 99 and 100%. You're the top 1% of the people taking the exam. You're in that top chunk of 80 students. Now we can say a similar thing about the 50th percentile. If you are in the 50th percentile, then your score is better than 50% of the people that have taken the exam. Or we could say that you're somewhere in the 50 to 51%, that group of 80 people that have taken the exam. And so a percentile is just take the data, split it up into 100 equally sized chunks, and then we can start to say things about it. Now, you might see some other similar words on the GRE that they sometimes use quartiles, in which we've split the data up into 4 chunks. So in this case, with our 8,000 students, they would be 4 chunks of 2,000 students. And again, we can say things about each of those quartiles. Far, far less likely to see it, but you can also talk about quintiles, splitting the data up into 5 equally sized chunks. In this case, that would be 1,600 students, or even deciles, splitting the data up into 10 equally sized chunks. And so in this case, We're dealing with percentiles, so each of our chunks is just going to be 80 students. Now, to help us with this question, I'm going to give us a bit of a bar here. Just a representation. This is not a technical thing or anything like that. What I'm going to say is at the bottom, I've got 0%, so nobody is going to score below whatever the bottom score is. And up here, I've got 100%. Everybody's below that. Now, the question tells us a score of P is at the 32nd percentile. So I'm just going to drop this in here. 32% P. 32% of people score less than P on this test. Okay, then we're told that there is some score Q. The Q is greater than P. Don't know how much greater yet. That's what the question's about. Score Q there. Now, the question tells us that there are 1,680 students who are between P and Q. We know that P is at 32%. And so the way that I'm going to find out what percentage Q's at, because that's what I want in this question, is to figure out how much of the total number of students is represented by 1,680. Or in other words, I can rephrase this as X% of 8,000 is going to equal 1,680. Now, converting this text into algebra, I get X over 100 multiplied by 8,000 equals 1,680. Or rearranging this, X is 1,680 divided by 8,000 times by 100, which if I get the calculator out and work that all out, that's going to tell me X is 21%. So this gap between P and Q is going to be 21%, which means that Q is 21% bigger than P, which is at 32%. So Q is going to be 32 plus 21%, or 53%. Now, percentiles are a little bit strange. The way that they're going to deal with the question is you can't tell whether 53% is bang on exactly where Q is, but the question's going to be phrased in such a way that we're dealing with approximations here. So that the answer choices are far enough apart, and we know that Q is there or thereabouts to be 53, and so we can say for this question, the answer is going to be C here. So, as I said, percentiles are just a way of splitting the data up into 100 equally sized chunks, and then it's a case of what are they asking you to do with it. This is one variation on the question, and I'm going to get another question up to deal with percentiles. We'll take a look at that. Again, another minute 45, and I'll see you back here soon to take a look at the next question. Okay, plenty to read in this question, so if you need any more time, now's your chance to pause the video. I'll take the question away so that we can work this one through together. All right, like I just said, lots of text, so let's work the question through from start to finish and see what we're told. So from the outset, we know that 100,000 teenagers from country A and 200,000 teenagers from country B had their heights measured. A height of 175 centimeters is at the 63rd percentile in country A. So 63% of the teenagers in country A had a height that was shorter than 175 centimeters. That's what that bit tells us. And it's at the 78th percentile in country B. So 78% of the people in country B had a height that was less than 175 centimeters. Then the question says, if we put these two populations together, what is the percentile, or a height of 175 centimeters would be at what percentile? Or in other words, what percentage of the total population would have a height that's less than 175 centimeters? So from this, we know that there's going to be 300,000 people in total. The challenge here is to figure out how many people have a height that's less than 175 centimeters when we push these two populations together. So first job, let's find out exactly how many people have a height of less than 175 centimeters in each individual country. So first of all, country A, this is going to be the easier one. 63% have a height less than 175 centimeters, and that's 63% of 100,000. So 63% of 100,000, well, that's going to give us 63,000 people. Country B, a little bit more complicated. We know that it's 78% of the people have a height of less than 175 centimeters, but it's 78% of 200,000 this time. Don't make that mistake and think it's 100,000 as well. There are 200,000 teenagers from country B. So 78% of 200,000 is going to give us 156,000 people, which means that in total, combined, there are 219,000 people with a height less than 175 centimeters. Now, in order to answer this question, I just need to know that as a percentage of 300,000. So the answer that I'm going to be looking for, 219,000 divided by 300,000, multiply the whole thing by 100, and you can either cancel all this down or get the calculator out, throw some numbers into it. If you work that out, that would come out to be 73%, which means that 73% of the people in this scenario have a height less than 175 centimeters, which means that 175 centimeters would be at the 73rd percentile, which means the answer to this question is going to be E. All right, so a couple of questions on percentiles there, and I hope that's made it clear that we're just splitting the data up into these 100 equally sized chunks, and then it's a case of how do you use them. If I talk about something being at, let's say, the 43rd percentile, that just means that 43% of the data, 43 of those chunks, are going to be smaller than whatever value I put on the 43rd percentile. And then, as you see in questions like this, we can go and use that information in various ways to answer the problems. So percentiles, we're going to put those to one side now. Final couple of questions, we're going to get into the normal distribution. Difficulty level is going to go up slightly in the next question, but it's the final one that's going to be really challenging. As ever, minute 45 on this one. I'll see you back here soon. Okay, pause now if you want more time for this one. Let's take that question away so that we can look at it together. All right, first normal distribution question of the video. So like we've done with standard deviation and like we've done with percentiles, I'm going to take just a minute or so to talk about the normal distribution and what the GRE is going to do with it before we go and answer this problem. So I've drawn a very rough normal distribution here. And as always with my diagrams, please imagine that they're better than I am. I'm no artist. This is meant to be symmetrical either side of the center. Right, so yeah, normal distribution, symmetrically either side of the center, and all of the data, whatever we are dealing with, in this case, we're just told a random variable p, but it could be something concrete. All of the data is represented by the area under the graph. Half of it to the left of the middle line, half of it to the right. In a normal distribution, the mean, the average, the mean is bang in the middle. So that vertical line tells us about the mean. 50% of the data is to the left, 50% of the data is to the right. After that, we can begin to talk about standard deviations. And the thing we're going to need for this question is how much of the information is included within one standard deviation, two standard deviations, and so on as we move out from the center. So what I can do is put, this is going to be the mean plus one standard deviation, and there's the mean minus one standard deviation. And I'll go one more, two standard deviations lower than the mean, and two standard deviations above the mean. Now, what the GRE will say, what the bit that we need for this is that for between the mean and one standard deviation above the mean is going to be 34% of the data. Similarly, on this side, 34% of the data is going to be here. So if I was dealing with, let's say, 100 items, 34 of them would be between the mean and one standard deviation below the mean, and 34 of them would be between the mean and one standard deviation above the mean. Or 68% of the data is within one standard deviation either side of the mean. Now we can go a little bit further. In this gap between one and two standard deviations out from the mean, I've got 14% of the data. And same on this side, 14% of the data over there, which means that in total, what the GRE wants us to work with is that 96% of the data is going to be within two standard deviations out from the center, which leaves us with 2% in each tail that's greater than two standard deviations out from the mean. So again, if I was dealing with 100 things, 2% of them should be two standard deviations below them, or more than two standard deviations below the mean, and two of them should be more than two standard deviations above the mean. So we've taken the normal distribution and we've split it up in that way. So that's all, that sort of can't get around it. I don't want to give you things to memorize, but this is just sort of one thing that there is no process behind it. Yeah, if you could just memorize this, you're going to be okay in questions like these. Because as you can see here, what we're going to get at, we've got, I'll convert this general diagram into one that we can use in this question. We're told that random variable p is normally distributed. So it's going to follow this pattern. And we've got a mean of 150. So I can put that number in there. Our mean is 150 and a standard deviation of 15, which means that this place up here, the mean plus one is the standard deviation, 150 plus 15, that's going to be 165. I can add on another 15 to get to two standard deviations, that's going to be 180. And I can reverse the process and go down the way, 135 and 120. And the gap between each of these standard deviations is 15. So what the question's asking us is the probability that the value of p is less than 120. Or in other words, what's the probability that the value of p is down here, more than two standard deviations below the mean? Well, as we just said, as we're setting this up, the chance you're more than two standard deviations below the mean is 2%. So with quantity A, I could treat this as a percentage and say that's 2%. Quantity A is going to be an eighth. And so, okay, if you can convert fractions into percentages fairly quickly, I can say that that's going to be 12.5%. Sorry, I don't know why I said quantity A there. That doesn't make any sense. That should be quantity B. Everything else in the question's nice, hopefully copied correctly, but that should have been quantity B there. So quantity A, as we said, represents the area that is more than two standard deviations below the mean. That should be 2% of the data, whatever the random variable P is that we're dealing with. 2% of it is going to be less than 120. Quantity B is 12.5% or an eighth. And so quantity B is larger than quantity A. So the answer to this question is going to be B. All right, so normal distributions, there isn't too much you need to know in order to get through the GRE using normal distributions. One part of it is, these numbers. Like I said, would love a way of getting around this without you just needing to memorize it, but there isn't really one. Okay, the GRE appears to, this is the setup they use in the textbook diagrams that I've been checking building this video. So this looks like the numbers that the GRE would like you to use for 1 standard deviation and 2 standard deviations out from the mean. You're using a normal distribution. If you can memorize these, as you can see, you can get through these sorts of questions relatively smoothly if you know this information. All right, I've got one more question for you in the video today. It's going to be another normal distribution one, but it involves some knowledge of how normal distributions work and how the curves work. This one's going to be a bit of a challenge if you're aiming for anything up to 165, maybe even a little bit higher. You probably don't need to be able to answer this one correctly. I'd expect this to be a bit of a challenge, but we'll see how this goes. As usual, minute or 45 or so. I'll see you back here soon to go through the last question for today. Okay, final question for today, and I expect this one's been a bit challenging. So if you want some more time, pause the video here. We'll still be here when you come back to us. So for now, I'll take this away and let us work through this problem together. All right, so I've only drawn the top half of the normal distribution here because that's all we're going to need for this problem. But let's dig into this and see what's going on, or at least dig into the question, see what information I can add to this normal distribution before we start figuring things out. So we've got the weight of a group of sheep. Okay, don't know how many sheep there are. Frankly, don't care about that. We just know the weight of a group of sheep is normally distributed. One sheep has a weight of 65 kilograms and is at the 50th percentile. 50th percentile, slap bang in the middle of our data. That's this middle line here. 50th percentile, that's going to be a 65 kilogram sheep. Another sheep has a weight of 85 kilograms and is at the 70th percentile. So I can put myself a bit of a line in here. Okay, that's going to be 85 kilograms. And I know that this middle line, that's the 50th percentile. And that line there, that's the 70th percentile. And now this question, the quantitative comparison question, says which is bigger. Quantity B is a bit easier to interpret, just 75 kilograms. I've got 65, I've got 85. The way that the normal distribution works here, the scale on the bottom, as you move left to right, this scale here goes up linearly. So the gap along the bottom between 65 and 75, I'll put 75 in the middle there, because the gap between 65 and 75 and the gap between 75 and 85 will be the same. Along the bottom, the scale goes up linearly. So I could have the same gap, that's 65 to 75, 75 to 85. I could keep going, 85 to 95, 95 to 105. That's predictable. The scale will continue in a linear fashion as we go up. Quantity A, this is where the challenge comes. I want to know the weight of a sheep in kilograms at the 60th percentile. I've got 50th percentile here, that was my halfway point, 70th percentile there. And now the question is, how do I split this group up so that I've got equal percentile within the data? And the difference here is that the percentile deals with the area under the curve, whereas the scale along the bottom moves linearly. So what I'm looking to do is split from the black line here to the red dashed line here, split that in half in terms of the area. I'll say that again. The percentile deals with the area under the curve, whereas the scale along the bottom just increases linearly. So I can put the 75 exactly halfway between the 65 and the 85 because that's the scale along the bottom. That's quantity B. In order to find quantity A, I want to split this area up into two equal-sized areas. Okay. Now, the challenge here is that this is a curve. It's a curved line. So I want, as I say, split this into two and the area under each of my sections to be equal. Now, the base, as we just said, we said all along, the base between 65 and 75 to 85 is the same. So I can't just put the line on the 75 because then I would have equal widths. But if you think about these roughly as rectangles, the rectangle over here would be much taller than the rectangle over here. And so the area on the left would be bigger than the area on the right. So I can't just split this on the 75 line. I don't know where the line is going to go. That's part of this. I can't be precise, but I know it's to the left of the 75. Because if I put a line in there and then roughly say, again, because this is a curve, and maybe it should be a little bit further to right just to make this clear. So I'll move it a little bit further. But if I put a line in there, then the shaded area to the left should be, and this is what I'm aiming for. I can't be precise about this, but I'm just trying to represent something. Is the shaded area the same area as this bit between the blue dashed line and the red dashed line? Now, as I said, I can't be precise. I can't tell you exactly what weight that's going to be, but the important thing is I know it's to the left of the 75. Because if it was bang on the 75, then the widths of both of those regions would be the same. But on the left side, I would have more height than on the right side. So the area of the left side would be bigger. So that blue dashed line must be to the left of the 75. And because this is a quantitative comparison question, that's all I need. Because I know the dashed blue line hits the x-axis, hits the base to the left of 75. I know whatever the weight of this sheep is, it's less than 75. So over on this left side, I've got less than 75 kilograms. Over here, I've got 75 kilograms. So quantity B is going to be bigger than quantity A. So the answer to this question is going to be B. All right, so this is about as challenging as the GRE is going to get with the normal distribution. It doesn't use any of the standard results we got from the last one. Like we said last time, so last question we were dealing with, where are the standard deviations? Well, that first one above the mean, we didn't get that until the 84th percentile. There's one standard deviation above the mean. So I couldn't have used any of the standard results in the last question. This question's all about the knowledge of the difference between the area under the graph representing the percentile and the linear increase in the base of the graph represented by the numbers. All right, so like I said, if you're aiming for anything 165 or down, maybe even higher than that, 166, 167 and down, you don't need to be getting a question like this right. This is right up at the top end of the difficulty level on the GRE. If you're aiming for perfect, then yes, you're going to need this. If you have to get to 170, yeah, you're going to need this sort of thing. But anything 165 and down, you don't need to get this right. I know this is challenging to see that difference between area representing percentile and linear scale along the bottom. All right, so there is a whistle-stop tour through standard deviation, percentiles, normal distribution. Yes, there's a lot here, but like I said, we don't need to get too technical. You don't need to know the formula for standard deviation, for example. There's a formula for the normal distribution. We definitely don't need to go anywhere near that. It's just about how the GRE is going to use it and what sort of questions they're going to ask you. So I hope this video has helped you see the sorts of things the GRE is going to do and has cleared up a couple of your issues. And yeah, so I hope this has been helpful, and we look forward to seeing you back here at another one of our videos soon. Thank you very much, everybody. Have a great day.